So hello, everybody. My name is José Pablo Folch. I am a recently machine learning graduate from Imperial College, machine learning PhD, and I am the co-founder and chief scientific officer of chemistry. We are a recent spin-out from Imperial College, and our focus is in enabling optimal condition selection in organic chemical processes. So what is the problem? Why solve? What are we trying to solve? And the question is, how can we produce chemicals the best way that we can? And as it has been shown in a few examples here, we have this high-dimensional parameter space when trying to produce chemicals. And it might include residence time, concentration, equivalence, temperature, what solvent to use. And we identify three main issues that the industry faces. The first one is that there is no existing large data set that we can kind of use to train models and kind of build. Second is that the data that we can gather can be, usually is gathered in a very inefficient manner. And third is that even though we know there's underlying chemical processes controlling everything, actually modeling this chemistry is very difficult. And so we want to resort to kind of using a machine learning or a black box function models that can kind of ideally predict things better. So what we're trying to answer most importantly is where is the data? And what our approach is actually to create the data ourselves. So we actually gather the data in our lab for clients. So we're not trying to just kind of provide like an optimization tool, but also just kind of actually leverage like efficient decision making. And our approach consists of machine learning aided experimental design. So we're trying to get information with less experiments, as the whole symposium is about. Also, we have efficient experimental data collection, which can be up to 20 times more efficient than standard kind of like batch collection methods. And we combine this with full automation in the lab to kind of gather data all the time as quickly as possible. And also, once we have a lot of data, it is to construct predictive models that can be very flexible. The benefits of our approach are less expensive and lower risk process development. Hopefully, we can enable implementation of more cost-efficient and more sustainable processes. In certain cases, we want to reduce the time to market for the product. And finally, it can also give you evidence to support processes to regulators because you have actual data backing up your decisions. The team consists of experts in machine learning and chemistry, and we are backed by Creator Fund, Imperial College, and Chemovate. We are relatively, we've existed for 6 months, so we don't have much to share, but I want to share quickly some advances. At the end of my PhD, I did this work on transition constraint-based optimization. And this is a base optimization when we have a constraint when moving through the space. And this algorithm allows you to select paths through the space so you can actually respect the transitions. We are currently testing this algorithm for the maximization of solvent selection. So we at Solve, we have a way of moving through the solvent space in a continuous manner using solvent ramping techniques. And we have benchmarked this using not base optimization, but actually design of experiment approach. And we've seen very good initial results. Okay, the next one's loading. Hopefully, I think it's okay.
That seems not loading. Let me just reset it for you.
If not, I can skip it.
Sorry about that.
No, it's fine. It was like a very heavy GIF that shows kind of like how we gather data in our reactors.
Let's give it a few seconds. Okay, we'll just put that in the post-event email so people can see that.
Yeah, that's fine. And then basically it was like similar to this, but just like the GIF version of how we gather data, and we can see how we move through the space, collecting data using this kind of transition constraints. And we are already like incorporating this algorithm and full automation into our laboratory. The open question I have for everyone is just how big data sets should be before they're useful, either for transfer learning or kind of to train models, kind of more general models in your experience. And yeah, thank you very much for having me.